conjugate beam method for predicting beam deflection uses a fictitious beam to represent reality, and that fictitious beam requires only statics in order to ultimately predict the deflection. And that's the advantage that makes this method appealing in some cases. In this problem, we'll predict deflection of a beam using the conjugate beam method, and the key concepts we'll use are generating M over EI diagrams and constructing the conjugate beam. And here's our beam. It's simply supported, pin at A, roller at B, with a cantilevered end out to C, with a couple moment applied at NC. This is exactly the same structure used in the example problem for double integration and moment area. EI is constant along the length of the member, and we want to calculate or predict the vertical deformation at C. And here are the steps we want to follow. First, we'll approximate the answer. So that we have something to compare to once we perform more lengthy calculations. We're going to need to calculate reactions. In order to construct the M over EI diagram. Then we'll be ready to create the conjugate beam. Which will be loaded with the M over EI diagram. And we'll calculate the moment at point C in the conjugate beam, because the moment at point C in the conjugate beam is our prediction of the vertical deflection at C in the real beam. Then we'll compare that answer with our approximation. Let's start by approximating the answer. Our predicted deflected shape will look something like this. That's also called the elastic curve. The quantity we're looking for is the vertical deflection at C, typically referred to up as a positive deflection. Now if we look at just the cantilever, we assume that end B was perfectly fixed, therefore no rotation, and we have a couple moment at the end. Then the slope starts out 0 and gets progressively bigger. So this is how we can approximate the real deformation. Now the difference will be this arching action between A and B leads to a rotation at B, and therefore the beam does not start with a 0 slope. It has a negative or downward slope already. So delta C will actually be bigger than our approximation, so we're going to have an underestimate. But the advantage of making this approximation is that a cantilevered beam with a couple moment on the end is a situation we can find in the front cover of our textbook, and there's already a pre-calculated formula for peak deflection, which occurs at the end, and that's what we're looking for, is deflection at the end of the cantilever. So let's use that. So we'll predict the vertical deflection at C is approximately a minus m naught L squared over 2 EI, where it's negative because the couple moment in our drawing in the front cover of the textbook is in the counterclockwise direction, opposite of this couple moment. So we'll get a negative. M naught being the couple moment applied, L being the length of the cantilever. In this case, 6 meters. We'll square that. Divided by 2 EI. And that quantity is a negative 900 kilonewton meter cubed over EI. So that fairly quick calculation will give us something to compare against after we spend a few more minutes trying to refine our prediction of deflection at C. Now we're ready to calculate reactions. We'll get a vertical reaction at A, a horizontal reaction at A, and a vertical reaction at B. Let some moments about point B. I can choose either direction to be positive for my summation. I'll choose clockwise as positive because AY contributes a clockwise moment about point B, and our applied couple moment is also clockwise about point B. I solve that for AY and get a negative 8.33 kilonewtons. It's not in the direction drawn up, but instead AY is down. I'll sum forces in the Y direction. I'll choose up as positive. I have a negative contribution from reaction AY and a positive contribution BY. Solve for BY and I get a positive 8.33 kilonewtons, and that is in the direction drawn. It's up. Now I can construct my M over EI diagram. We'll start with shear diagram for the structure. We have a downward reaction at A to negative 8.33. We have no applied loads between A and C, so the shear diagram is constant. Then we have an upward jump of 8.33, so we had a negative 8.33 plus 8.33, and we close back to 0. We have no distributed load, no applied loads between B and C, no forces rather, between B and C, so the shear diagram remains constant at 0. Now the moment diagram. At the pin at A, it starts at 0. And then our shear is constant and negative, so my moment diagram is linear and getting negative. And it stops at a point that is the original moment, 0, plus the area underneath the shear diagram. So we have a 0 plus the negative 8.33 kilonewtons through 6 meters, and that gives us a negative 50 kilonewton meters. Then from here, the shear is 0, which means the slope of the moment diagram is 0. We have a constant moment. And then we have a clockwise moment applied, which is a positive jump in the moment diagram. We had a negative 50, we added 50, we get 0. And it closes to 0 the way it should. Now we'll divide that moment diagram by EI, and EI is a constant for the whole beam, so it'll have exactly the same shape. Linear down to point B, constant over to C, and back up. And its peak negative value, a minus 50 kilonewton meters over EI. And just to be complete, I'll put the units back on my vertical axes that I intended to write up there but forgot. Great. You can now create the conjugate beam. Which will replace the real beam and the real loading. To do that, we're going to use the help of Table 8-2 from our textbook. The real beam has a support at the end that's a pin, so in the conjugate beam we'll start with a pin. We then have an internal support, internal meaning not at the far ends of the beam, at B. So an internal roller will be modeled in the conjugate beam as a hinge. So we have a hinge at B. And then the free end at C. A free end in a real beam is modeled as fixed in the conjugate beam. And then we apply the load, which is M over EI. And that diagram was negative, so this load is applied down. And the peak magnitude here is a negative, or already drawn down, it's 50 kilonewton meters over EI. Now, even though this structure is indeterminate, because it has one extra support degree of freedom in the x direction, this loading doesn't cause loading in the x direction, so we can consider that like a roller, and then this is a determinate structure. Now it's time to calculate the moment at C in the conjugate beam, so I'll call it MC prime, which is my prediction for vertical deflection at C. Let me redraw our conjugate beam, making the substitution at the end. So that we can see we have a determinate beam, and that segment is 6 meters long, this segment is 6 meters long, and it's loaded downward with a distributed load, distributed conjugate load, 50 kilonewton meters over EI being the peak value, which is constant over the second part. Let's cut this beam at point B, the internal hinge, and draw a free body of AB. And my vertical reaction, AY prime, my shear at the hinge B, VB prime, and my distributed load, which increases linearly to 50 kilonewton meters over EI in the downward direction. Ultimately, I'm looking for the moment reaction at C, so I really don't care about the reaction at A. I need the shear at B before I look at the next free body. So let's sum moments about point A. We'll call it A prime because this is the conjugate beam. I can choose any direction to be positive. I'll choose clockwise to be positive. That gives me a positive contribution from the shear at B prime through 6 meters, plus the contribution from this distributed conjugate load, and that's triangular, so we have 1/2, the base being 6 meters and the height being 50 kilonewton meters over EI, and that is clockwise about point A. We'll solve that for the shear at B prime, and I'll get a negative 100 kilonewton meters squared over EI. So that's the shear at B prime in the conjugate beam. Now let's draw a free body, and that was A prime and B prime because this is the conjugate beam. Free body diagram of B prime to C prime. I draw up but have a negative 100 kilonewton meters squared over EI is the shear at B prime. I have a downward applied uniform distributed load of 50 kilonewton meter over EI. I have an unknown vertical reaction CY prime and unknown moment reaction MC prime. And so again we'll sum moments, this time about point C prime, and this time I'll go counterclockwise as positive, set that equal to 0. I have a negative contribution, but the magnitude of the shear at B prime is negative, and that acts through 6 meters. Then I have a positive contribution from the distributed load, 50 kilonewton meters over EI times 6 meters. That makes it a force, and then acts through a distance of 6 meters divided by 2, or 3 meters. And we get a positive contribution from the unknown reaction MC prime. We'll solve that for MC prime and get a negative 1500 kilonewton meter cubed over EI. And remember, because this is in the conjugate beam, that is our prediction for delta C. Now we can compare our result from the conjugate beam method with our approximation. We had said that our approximation for the vertical deflection at C was a negative 900 kilonewton meter cubed over EI. We said that would be an underestimate. And then we just saw, using conjugate beam method, that we predict a negative 1500 kilonewton meter cubed over EI. And so this is a slightly larger deflection than our underestimate, and it's only about 50% larger, so it's not orders of magnitude different, That's a pretty convincing argument that we have a reasonable result. But in addition, another approach to ensure a reasonable result is to use different methods to predict the result. And if you look back at our example problem for double integration and our example problem for moment area, they were all predicting deflection at C for this beam, and all three come out with exactly the same quantity. That also is a good indicator that we have a reasonable result. Well done. Now let's go back and review how we used the conjugate beam method to get to this prediction of deflection. We started by predicting the deflected shape, or drawing the elastic curve for the beam, and we said this segment of the beam can be approximated by something we see in the front cover of our textbook, which has already got a formula for deflection. We use that to create an underestimate of the vertical deflection at C. We then calculated the reactions and constructed the M over EI diagram. We were then ready to create the conjugate beam, and we used table 8-2 from our text to know how to create a beam that would behave in just the right way to predict deflection if loaded by the M over EI diagram. And so our real beam became the conjugate beam with a pin, hinge, and fixed support. We applied equilibrium to that conjugate beam in order to calculate the moment reaction at C in the conjugate beam, and that moment reaction in the conjugate beam is our prediction of vertical deflection at C. We then compared our result with our approximation, found that it was in good agreement, and concluded that we have a reasonable result. Another method we used to conclude we have a reasonable result was to compare this result with the result we obtained from another method, like moment area or double integration.